Thank you for that answer. And since you mentioned quantum mechanics, I thought I'd get your thoughts on causation, because this is something in which we can, as philosophers, say, scientists can be helped. Their method of reasoning can be facilitated through, distinctions about different types of causes and what it actually means. And obviously, that's linked to the whole concept of randomness and what exactly that means. And this is something you've spoken about before, but I think it's worth going into again.
Yeah, it's a great question. It's a little complicated because there are so many moving parts, including quantum mechanics itself, which is something that everybody claims to understand, but probably very few people, if any, actually do. So here's the thing in terms of causality. If we're talking about all the sciences except fundamental physics, so setting aside for a moment quantum mechanics, causality plays a major role. I mean, everything that we're interested in as sciences is causally grounded. And in fact, a big way of understanding phenomena is precisely when you can establish causation, right? So, for instance, let's take simple examples. Does smoking cause cancer, or is it just statistically correlated with cancer, right? Well, we think we have, because of a number of observational and experimental evidence, we think we have good reason to conclude that cancer is actually causally connected to smoking. It's not just the correlation. And a lot of what's going on in the sciences, especially in the so-called special sciences, such as biology, certainly all the social sciences, etc., a lot of what's going on there is, in fact, the attempt to distinguish correlation from causation. Right? So causation is a fundamental concept. But what is causation? What is a cause, right? Well, that's not a scientific question. You cannot do experiments on causation itself, right? You assume causality as part of your view of the world, but you cannot actually do experiments on causality itself, which right there, it's another example of, here's a question that is not scientific, it's important, but it cannot be answered scientifically. Now, in philosophy, metaphysicians have come up with a number of alternative conceptions of causality. I think the last time that I checked, there are at least a dozen different conceptions of causality. One of my favorite is that causality happens every time that there is a transmission of a conserved physical quantity, such as momentum, for instance, right? Or energy and stuff like that. So, for instance, two billiard balls bump into each other. Well, one moves the other. Why is that? Well, because there is a conservation of momentum and energy in between the two, right? So kinetic energy is transformed into the kind of energy that moves in more kinetic energy plus friction, which moves the second ball. Great. That's certainly one interesting conception of causality. But there are others. It's not the only player. And these conceptions are useful to think about what causality is and how it works, but again, you cannot do experiments on them. Now, what about quantum mechanics? Well, it turns out that in quantum mechanics, if you enter the realm of quantum mechanical theory, there is no talk of causality. Quantum physicists don't talk about causality. They don't need the concept. Does that mean that it doesn't exist at the quantum level? I don't know. I don't think actually anybody knows. And the reason nobody knows is because at that level, things begin to break down. Concepts that we use normally at a microscopic level begins to break down. Let's not forget that nobody really has come up with a reasonable physical interpretation. Sorry, I should say not reasonable, with an universally accepted interpretation of quantum mechanics. Nobody. There are a number of interpretations out there. There's like 20 plus, the many worlds, the Copenhagen interpretation, there's a bunch of them. But nobody has come up with an interpretation that seems to be compelling to everybody else. In fact, so much so that there is a school of physicists who call themselves the shut up and calculate school, which basically say, look, quantum mechanics is just a bunch of equations. And all you can do about it is to plug those equations into experiments and come up with very, very precise predictions about the outcomes of those experiments. But if you ask yourself the question, what do the equations mean in a physical sense, you're just asking the wrong question. It's just, They're just equations. It's a model that works, and that's the end of the story. Now, I sympathize with both schools, for both approaches. At the moment, it is certainly the case that quantum mechanics is a bunch of equations. That's true. And those equations are open to a number of interpretations, which tells you right there that there is no straightforward physical interpretation of the meaning of those equations. But it is unsatisfactory, because in everything else in science, we want to know, well, what does that mean? When, for instance, in general relativity, when Einstein, general relativity also is a bunch of equations, right? But physicists didn't stop there. They said, oh, well, but what those equations mean is, for instance, that gravity is the result of the deformation of space-time, which is caused by the presence of massive objects. Okay, well, that's satisfying. That gives a physical interpretation, one on which physicists seem to agree, for those equations. We do not have a similar thing in the case of quantum mechanics. Until and if we're going to have such interpretation, I think that it's a little premature to say that causality doesn't play any role at the quantum level. We just don't know, because we don't have a good physical model for the quantum world in our minds. We may never have it. So all we can say is the concept of causality doesn't seem to be useful at the moment for current interpretations of quantum mechanics. Fine. That doesn't mean that causality is or is not there. It's also possible, of course, that causality is what people refer to as an emergent property. That is, that it doesn't actually, like wetness for water, for instance, right? Individual molecules of water are not wet. They're just molecules of water. But if you put a bunch of them together, then you get the property of being wet, or the property of changing status at a particular temperature and stuff like that. Okay, well, so that's an example of the fact that some physical properties do not necessarily exist at lower molecular or submolecular levels, but they do emerge. And I don't mean this in any kind of mystical sense. They emerge in the sense that they were not measurable before, and now they are. Transition states, for instance, in physics, are measurable only when there is a large number of particles. So the thing that water at certain temperatures goes from solid to liquid, and then from liquid to gas. Well, that is not the case for individual molecules. It's not the case for if you only have a few dozen molecules of water, but it is the case if you have millions. Okay, that's something we can describe. That is a very good example of the fact that some properties exist at one level of analysis and don't exist at another level of analysis. Maybe causality is like that. Maybe causality does not exist or does not play a meaningful role in our understanding of things at the quantum level, but it emerges for macroscopic systems.
Yeah, that's